So you are on a spaceship and you encounter a sentient alien who has never been to Earth. And they ask you what Earth life is like. And what do you say? So tell me what you would say. Just quick, a couple things that you know about Earth life. Yes. There's water. Great one. What else? Yeah, carbon-based. Okay, so you guys know something about Earth life. I'm going to give you the complete list, and you can take it home. So there are a lot of really important things about Earth life that can help us when we're thinking about whether or not we would find Earth-like life on other planets, which is kind of the theme of this talk. So it's carbon-based. Why is that good? Well, because carbon is really abundant in the universe. We know that it's very abundant. As are other common elements that make up life. So nitrogen, sulfur, iron, all of those are pretty common elements. So leaving us to believe that it would not be very hard to reproduce Earth-like life potentially in other places. Requires liquid water as a solvent. Why is that important? Well, it sets a bunch of the limits, the hard limits for life if you require to have a liquid solvent. So we're going to come back to that. One of the main things about Earth life is that there are two ways of making energy. One way is from starlight. So organisms on Earth have learned how to harvest starlight. And then another way of doing it is from electron transfer reactions that are at disequilibrium. And luckily for us, life forms, the rates of reaction, of redox reactions, vary by 20 orders of magnitude or more. So there are lots and lots of redox reactions, electron transfer reactions, that are very, very slow. And microbes take advantage of that and speed them up, harvesting energy in the process. You notice that there's an electromagnetic spectrum on the bottom of this slide. And I've blown up the visual part of the spectrum. And that's essentially the same part of the spectrum of starlight that Earth life can harvest. Isn't that interesting that your eyes see the same piece of the electromagnetic spectrum that photosynthetic organisms can harvest? That is not an accident. So on this high energy and the UV end, what's wrong with UV? UV, we know it's bad for our skin, right? Causes cancer. UV wavelength is the right wavelength to interfere with bonds. So it's not good for cells because bonds are broken by those kinds of wavelengths. So that's why it's not used. On the other end of the spectrum, getting into the infrared, that can't be harvested because it's too low energy to move electrons out of their stable orbits into high energy orbits that we need in order to do photosynthesis. So that's some physics and chemistry that is setting those limits on what kind of starlight can be harvested by Earth life. All right, so here's a quick list. We're not going to go through all of these. Carbon-based requires other common elements, requires liquid water as a solvent, harvests energy from starlight in the visible range or electron transfer reactions that are at disequilibrium in the environment. It's sensitive to UV. A couple other things that are bad as well. Anything shorter wavelength than UV, as well as cosmic rays, which are things like protons and heavy atomic nuclei. But luckily, we're currently shielded from those things by what? The ozone layer and the Earth's magnetic field. So you might, when you're thinking about life on other planets, you're going to think about whether or not there's a magnetic field and whether or not there is some kind of atmosphere that will shield other kinds of harmful photons from the surface. We know that life evolves. That's a fundamental feature. It evolves in response to conditions in the environment. And it has a cellular organization. You might not think about this very much, but there is no life form on Earth that is not made of these units called cells. And it seems like a no duh, but it's actually, there are other ways that you could do it. So life is cellular here. All the cells on Earth today share a common ancestor, which is a pretty remarkable thing when you think about it. And related to that, we have the same genetic code. Not only the same genetic code, but we use the same molecules to encode that. So, and we also have a common energy and currency involving high energy phosphate bonds. And that's ATP, adenosine triphosphate. So that's a lot of things in common. So really cells are just cells. Largely, all these cells are the same. So just a few illustrations of that. Here's a piece of ribonucleic acid. That's part of the machinery and the information that we need to build cells. And on the right is a diagram that shows you how every cell on Earth translates nucleic acid-based sequences into amino acid protein sequences. So all cells do that the same way. Okay, what else can you say about Earth? One of the things that I had not thought about for the first half of my career, and now I think about it a lot. Life is very old in relation to the age of the universe. So we've been pushing back slowly the date for the best evidence for the first life. And so we're now very confident that there was life around 3.5 billion years. And there was liquid water by at least 4 billion years. So sometime between 4 billion years ago and 3.5 billion years ago, life started up. So that is old in relation to the age of the Earth, right? Life started up really fast after the Earth cooled down to a temperature where there could be liquid water. I think that's remarkable. But also, it's old. Earth life is old with respect to the age of the universe. So here's the whole age of the universe. Here's 13.8 billion years. Here's the Big Bang. The first stars don't form for about 1.5 billion years or so. And here's the time of the formation of our solar system. So that's a good chunk of the age of the universe. So Earth life is really, really ancient. And our solar system in general has been around for a very long time. So at least a third of the age of the universe. So we've been around. Okay. Another thing that's important about Earth life is that it's mainly too small to see with human eyes. And I'm going to illustrate that point in several different slides. So the life that you can see with your eyes, here's a phylogenetic tree that shows evolutionary relationships between all of the extant life forms on Earth. It's very simplified. You can see here, this is a 1980s view with three domains of life: bacteria, archaea, and eukaryotes. So that little twig right here that says Homo, that's our genus. That represents all of animals. This Caprinus, that's a fungus. That's all of fungi. And this Zea, that's the genus of maize. And that represents all of plants. So in this diagram, the life that you can see with your eyes is right there. And everything else is microscopic. So yes, you see a lot of macroscopic life around you. So in terms of biomass, macroscopic life is very significant, especially at the Earth's surface. But in terms of the diversity, the number of tricks, the number of reactions that can be harvested for energy, all of that diversity is microscopic. Okay, here's a more modern view of the tree of life. You can see it's kind of collapsing into a two-domain situation. So this is bacteria. And all of this purple stuff here, and these purple lineages in there, those are things that we first met in the last 5 years. So we are not done discovering new life forms, far from it. Likewise, there's a lineage called Depan in the archaea. This is the archaea that was just discovered in the past couple of years. You can see here that eukaryotes have collapsed down into the archaea. So it's clear now that eukaryotes arose from archaea by some kind of hybridizing process with, there's some bacterial involvement there. So eukaryotes are this branch here, and even eukaryotes are mostly microscopic. And this is just an illustration of some of the diversity of prokaryotic or eukaryotic life. And this is an image showing you a giant bacterium. I'll admit it's a very big one. So it's on the big side of bacterial scale. But these are protists. So lots of protists or single-celled eukaryotes are very, very small. They're bacteria size. So we're finding now that some of the methods that we use to study microbial life in the environment have been really biased toward large cells. And this is microbiologists doing this, right? We have filters that are letting half of the biomass through because their cells are too small, or we have centrifugation protocols that are not long enough or high enough Gs to sediment the cells that we're interested in. So our methods are changing as we realize just how small cells can be. And according to the National Academy, cells can be something like 0.1 to 0.2 microns. That's 100 to 200 nanometers in diameter. That's the minimum size, and we've already found living, reproducing cells that are that size. So we have to, we've been focused on this kind of 1 to 10 micron size range, but we have to be paying a lot of attention to even smaller organisms. Okay. Another important thing about Earth life is that information trading and the exchange of energy are in the form of chemical compounds. It's very common. It's very characteristic. It's not unusual. It's the norm. So these are just pictures of very closely associated populations of cells, and they're as close together as they can get, so that it's easier to trade information and energy compounds. And this is a very common thing in nature. And it may be one of the driving forces for symbiosis. So symbiosis is also the norm rather than the exception on Earth. This is a timeline that shows you, here's the formation of the Earth and here's the present day. And so sometime, this is really poorly constrained, even today. Sometime in this time range, eukaryotic cells acquired what would become mitochondria. And in addition, a eukaryote with the mitochondrion then sometime slightly later acquired a photosynthetic symbiont that was derived from a cyanobacterium. So this scenario here, it looks pretty complicated, and it actually is, because these are not singular events. These are events which may have happened many times. And it's difficult to sort that out because it happened so long ago. But with the plants especially, you can have primary and secondary and even tertiary symbioses in which algal cells engulf other algal cells, spit out the guts, and keep the symbiont. So this happens all the time. There's symbiont hijacking going on right under our noses. Okay. So just to sum up that bit that we've just gone over, and a few more things. Life on Earth is very old, mainly too small to see. We didn't talk about this, but there's considerable controversy about just how many different species there are on Earth. I'm going to skip over that because it'll drag us down. There is a lot of gene exchange, information and energy exchange, and that's a driving force for symbiosis, which is also very common. Interesting fact, all known cells are infected by viruses of some type. So don't feel bad. It's not just you. It's all cells on Earth. And this is the last two things are things that I think are very interesting from the point of view of subsurface life. There's a term called the biological energy quantum, and that is the quantity of energy that is harvestable by a cell. So it's some kind of chemical energy in some amount that can be conserved by a cell machinery. And that energy quantum is at least as low as 10 kilojoules per reaction. And to give you some kind of scale there, you might be, your stomach might contain some glucose molecules, you're breathing in oxygen, and your mitochondria are burning that glucose with oxygen. From that reaction, you get something like 3,000 kilojoules per mole. So we're talking about a very small amount of energy that can be conserved and sort of sequestered by biological machinery. There's a related term here called the Basal Power Requirement, and that's the energy required per cell to kind of fight the forces of entropic doom. So the molecules that make up your cells are not stable at Earth's surface temperature and pressure. They're trying to fall apart, and the cell has to expend some energy in order to keep things in order. And so that Basal Power Requirement, if it's met, it's possible that a microbial cell could live for tens or hundreds of millions of years. So that's a very significant piece of information. All right. we're now going to switch gears. You're going to take all that information about what Earth life is like, and you're going to think about what I'm going to tell you next. And then you're going to also think, I hope, about whether or not these kind of subsurface environments that I'm going to talk about could be found in other places in the solar system or around other stars. And I'm not going to answer that question. We obviously don't know the answer, but there are some interesting examples from the Earth's terrestrial subsurface I think are relevant. So I go in caves a lot. Caves are just subsurface voids that are big enough to admit humans. And there are a number of reasons to go there. They're windows, essentially, on processes that are happening more broadly in the subsurface. But they also can be hotspots because there are big voids. That means it can be a lot of fluid flow. And one of the things that you can do to make chemical energy available is to mix fluids. So if you can mix fluids in the subsurface, that is a potential dynamo that can support subsurface life. So these are some caves. This is actually an ice cave in Svalbard. And these two pictures are from a cave in Italy where we go a lot. So big enough to admit humans, the cavers love to test the limits of that. And so their voids can be, person size, or they can be 300 meters deep. So these are kind of extremes of what the scale of what subsurface voids can be like. Oh yeah, this is my former PhD student, Dan Jones. He did get out. So how do caves form? Where do they form? Why do they form? Caves form in rocks that we call soluble, rocks that we can get to dissolve at Earth's surface temperatures and pressures. And lots of people think first about rocks that are made out of carbonates. There are some other possibilities, but the main story here is that caves form in carbonate rocks. So those are the bright blue areas of this map. And you can see there's quite a number of places on this Earth where there are lots and lots of caves. To bring it closer to home, here's a map of the United States. And limestone is shown in that blue color. And there are also caves that can form in salts, so in evaporites like gypsum. And that's also shown here in the green. And then there's a third kind of cave that is formed in volcanic bedrock by really very different kinds of processes, and that's shown in pink. So where are we in Pennsylvania? We're here. We have sinkholes, and we have lots of carbonates, so there are lots of caves all around you. Okay, so most caves on Earth form by the action of soil CO2, which is concentrated by decomposition of organic matter that's fixed at the surface by plants. And that CO2 percolates downward, dissolving carbonate as it goes. And these are some examples of surface landforms that result from that process. So these are typical Earth caves. They have these superficial sort of expressions of the process that's forming the cave. This is the deepest cave on Earth right now. There's a big race going on to see who can be the deepest. The runners-up are in Mexico. This is the Krubera Cave in the Caucasus Mountains, and it's currently greater than 2 kilometers deep. So in order to have a cave like that, you have to have a really thick deposit of carbonate rocks. So that's important for thinking about caves on other planets. Little known fact, silicate rocks can actually form caves, even though we don't really normally consider them to be soluble rocks. So there are some very old landscapes in the tropics where caves have formed in silica-rich sedimentary rocks. And they have really distinctive microbial communities in them. So when you think about how surface conditions might be influenced by the presence of these big conduits, I was saying before that if you have cave forming processes, you can get fluids to mix. So it's a way to get stuff from the surface quickly down pretty deep, up to 2 kilometers deep, in a place where ionizing radiation and UV can't really reach. So if you can get conduits to form, then you can have this protected environment where nonetheless things from the surface can flow by gravity into that deeper place. And the conduits just make that able to be happening much more quickly. So here's an example that shows what the time scale for cave formation is. So something between 1,000 and 10 million years. So this is really interacting with the plate tectonic time scale. So lots of times you find expressions of plate tectonic movements in the morphology of cave systems. So in this case, you have the oldest cave levels that higher up, and you have a downcutting fluvial system here. And so maybe there's also tectonic uplift that's speeding that up. You can have really some interesting interactions with plate tectonics that can enlarge and make these caves form more quickly. Okay, so I'm really plugging caves here, but really most Earth caves are really biological deserts. They have very low biomass. All the life is really cryptic. It tends to be not showy at all, hard to find, it's hard to study, it's very slow growing. And when you analyze what's there, the slowly growing stuff, it looks like stuff that filtered down from the soil zone and is just eking it out down there. Not the kind of thing that would cause you a lot of excitement when you're thinking about a subsurface biosphere on Mars or on another planet. This is not what you want. This is a slowly dying biosphere that is barely making it on stuff that's washing down or being brought in by bats, if you're lucky. So this is not what I study, although there are interesting things about this. So we're interested in this biological power requirement and this biological energy quantum. Those are things that you can study here. And those are it's not what I study, but it's an interesting thing to do. Okay, so I told you one way that caves form, most Earth caves form by this soil CO2 dissolving carbonate rocks. There's another way to do it too. Actually, there's 3 ways. So here's a second way. If you mix 2 waters that have different origins, you can get carbonates to dissolve just because of the nonlinear effects that occur due to the redistribution of carbonate species. So if you mix these 2 end members, you can get dissolution to happen. And this is part of the wackiness of carbonate chemistry. But it works great. And where do you see this happening most? Along coastlines where seawater and freshwater are interacting. That's why a lot of recent carbonate platforms are like a Swiss cheese, because there's rainwater, it's close to sea level, and you get all this sloshing, tidal action, sloshing this rainwater and the seawater together, and then you make really big holes in the carbonate platform. An example of that is the Bahamas. This is showing you cave entrances. Some of them are obvious and some of them less so, but it's really a Swiss cheese. Been corroded by this sloshing around and this mixing of 2 waters. Okay, the third way that you can form a cave is by hypogene processes, and I hate that word, it's really jargony. It just means forming from below rather than epigene, which means forming from above. So most caves are epigene. There's this other whole class of caves that are called hypogene, and they form in a variety of geological settings. So they form near oil fields. They form at weathering fronts in coal, shale, and other pyrite-rich marine rocks. They form in carbonate-hosted, sulfide-rich metallic ores like Mississippi Valley type deposits. They form in marine carbonate platforms. They can also form in subglacial sediments with mixed lithologies. So if you grind up a rock that had pyrite in it and a rock that had carbonate in it, you can form a cave that way. Yeah, there's a couple of other ways to do it. We didn't talk about ice caves yet, but we will. But here's a kind of a classic example of a hypogene cave, a cave that's forming from below, still involves mixing water. That's really important. So in this case, I'm showing you a cross section through a big, massive limestone, and you can see that there's a water table here, and the groundwater is sulfidic. And how did it get sulfidic? Well, we'll talk about that in a second. But you have percolating meteoric water that's filtering downward. And those two waters have very different chemistry. And not only do they have different carbonate chemistry, so they can dissolve limestone that way, but they also have different redox chemistry. So this is a place where there's a ton of chemical activity that's catalyzed by microbial life. And so H2S is coming from below, oxygen is coming from the top. This is a really profitable redox reaction energetically, so microbes can harvest that energy and make a living. And it makes this place really a slime palace. This is just some evidence that those waters are mixing. So here are what we call type 1 sulfidic waters, places where the sulfidic aquifer is less mixed with rainwater. Here's drip water that's in the upper portions of the cave, far away from the sulfidic water table. This is essentially rainwater with a little bit of salt in it. And then there's all this mixing. So there are a lot of places in this cave where you can find mixed water, where you can find both sulfide and oxygen present at the same time. Okay, I'm gonna skip that. I'm gonna skip that too. So here's a map of that cave. And you can't see because the legend is cut off. This whole map is about 2 kilometers in width, and there are about 25 kilometers of navigable passageway so far in the system. And you can see that some of the passages are, they're 100, 200 meters wide. And so this is a big, big system. But it's not anywhere near the biggest cave that formed by this mechanism. The biggest one we know about is La Chuvilla Cave, which is in New Mexico. This cave has 200 kilometers of navigable passage, 400 meters in depth, and it's just spectacularly big. Okay, I said this before, hypogene caves typically host these very conspicuous, not cryptic, very conspicuous microbial ecosystems. They're based on lithoautotrophy, or harvesting chemical reactions from the environment and fixing carbon from CO2, but in the dark. Lithoautotrophy. And so these are all pictures from that one cave that I gave as an example, where we go often. So these are just examples of situations where there's these conspicuous biofilms, and they're transforming chemicals into minerals in some cases. So here's biofilms that are producing elemental sulfur that your eye is seeing as a white color because it's very small particles of it. Here's a biofilm that is in a different part of the aquifer, a different depth zone, and it's making iron monosulfides. Here's a subaerial biofilm, so not underwater, in the air, that is making gypsum. And here is a type of biofilm even farther from the sulfidic water table, in the air, where there are organisms that are somehow involved in the precipitation of carbonate minerals. And so those are all in the same place. Okay. So hypogene caves, really interesting from a subsurface biosphere point of view. If you can somehow get fluids to mix underground, you can have quite a bit of biological activity in the subsurface. And now I want to switch and talk about lava tubes for a minute, because lava tubes are really interesting from a Mars perspective, from a couple different angles. We're just going to let you see a couple pictures of lava tubes. They're forming by an entirely different mechanism. These are not soluble rocks. These are caves that are formed by lava cooling on the outside and then continuing to flow molten in the center until the tube drains away. And you're left with this type of cave. So these can be very spectacular and large. Here are two people for scale. And this, you can see the ceiling of this lava tube has collapsed. This is Mauna Loa in Hawaii. And I want you to look at the shape of this. And I'm going to compare it to a picture that's taken from the Mars orbiter. Okay, lava tubes. What about life in lava tubes? Well, there is life there. And there is also secondary mineral precipitation. And there are lithoautotrophs, which means that you can have primary production underground. And therefore they're quite interesting. There are water ice caves. And those can take a number of forms. They can be hypogene, they can be hydrothermal, lots of different situations, lots of them on Earth. So here's the global distribution of glaciated Holocene volcanoes, so volcanoes that are still active hydrothermally, and if they're glaciated, there are going to be ice caves there. And why is that interesting? It's interesting because you can have hydrothermal activity and ice, which is going to protect you from radiation. So a nice situation. Okay. How can you predict how much life is going to be underground in these situations? Well, it depends on how much chemical energy flux is there. And that lots of times depends on fluid flow. So once again, it's kind of about getting fluids to move around so that they can interact with each other. So here's an example from Romania where there is an aquifer that is connected to the Black Sea. And the Black Sea has this anoxic bottom water, and it's got methane and sulfide in it. And there's a really spectacular microbial ecosystem in this cave that is cycling methane and sulfur. This is a really interesting one. And this is so far pretty uncommon. There's not a lot of reports about this, but this is Wee Bubby Cave, excuse me, in Australia. And this is hosting an ecosystem that is almost entirely running on the nitrogen cycle. And so there are nitrates in these evaporitic plains up above the cave system, and the nitrates are leaching down into the cave water. There are portions of that aquifer that are anoxic, and the nitrate is reduced. And then there are other parts of the aquifer where the ammonium that results is reoxidized, and so there's this whole nitrogen cycle that appears to be almost the only thing really fueling this ecosystem. But it's very conspicuous. You know, it's like slime palace down there. Here's a situation where the life is being fueled entirely from the air. So when I say get fluids to move, air, gases count too. So in this case, there are H2S vapors that are degassing from the aquifer surface. And then there is enough, the cave breathes enough that there's plenty of still oxygen left in the atmosphere. So there are mixing of different gases. This is an entirely gas-fed community. It's pH 0. It's getting H2S and O2 and CO2 and ammonium from the air, from the gas phase. So this is an entirely kind of gas-fed community, which is a little weird. Here's another underwater situation where there's both an iron cycle and a nitrogen cycle that are very much interconnected. So this is a cave in the Dominican Republic where the iron is coming actually from Saharan dust. So fluids moving, the iron from the dust in the Sahara lands in the Caribbean and is fueling this subaqueous cave ecosystem. Also very slimy down there. Now, what if you can get skylights and we can get starlight into this environment? You can get a whole host of other different kinds of phototrophic communities that are also fixing carbon in the subsurface. Maybe not what you first think of when you think cave, because you think permanently dark, but there are lots of subsurface voids actually that starlight can get into. And so here's a situation. This is a sinkhole in the Bahamas, and what you're seeing is a phototrophic layer that's super dense. It looks like pink Kool-Aid when you bring it up. And these are anoxygenic or non-oxygen producing light harvesting bacteria growing to very dense populations. And when they die, they're feeding a whole ecosystem in the anoxic bottom water below them. this is the view looking towards the sun of a biofilm that is essentially harvesting light in the dark. So this is another sinkhole in the Bahamas. Those are divers up here, and you're about 40 meters down. Usually you would not be able to have much light at that depth, and in fact, there is not much light. The divers are essentially in the dark, but you can see them here. They are cutting up a piece of this lasagna-like biofilm to bring to the surface. You can see it's got pinnacles, and it's this highly pigmented, kind of thick biofilm. And we've studied that biofilm a little bit, and it's called magical blue hole. It's got a pinnacle mat that's thickest at 30 meters. And when you measure the amount of photosynthetically active radiation or visible light that's reaching the biofilm, the answer you get is 0.09 to 0.0001 micromoles of photons per meter squared per second, which means nothing to you. But for comparison, the most light-starved, light-harvesting bacteria so far were these organisms that were cultivated from the Black Sea hemocline. So at about 100 meters depth, and they're receiving more photons per time per area than this blue hole biofilm. So same order of magnitude, but we won. So in this situation, if you're an organism and you're harvesting light using molecules called bacterial chlorophylls, every bacterial chlorophyll molecule absorbs on average 1 photon every 8 hours. That's ridiculous. That's super duper slow. It's also interesting to note that I said it was interesting to study things that were starving, and we do a little bit of that in this case, because organisms that are adapted for these kind of low energy flux environments also have, so far, really low basal energy requirements. So that's interesting because it kind of sets this lower limit on how slow can you go and still be turning over and harvesting light. Okay, let's see here. I'm going to talk about a subglacial cave system for a minute, just to give you one more example of the kind of environments that you could think about. So think about the polar ice cap on Mars and what might be underneath that. And so people go to places like Svalbard to try to understand the dynamics of what's happening underneath ice sheets and what microbes have to do with it. So this is the entrance to one of the caves on Svalbard, the ice caves. This is essentially a glacial melt conduit. So water ponds up on top of the glacier. The water has a high heat capacity and eventually melts through to the base of the ice sheet and then goes downhill to the ocean underneath the ice sheet. And so it looks like this, a bit scary. There's blocks of ice falling. These streams are just raging through here. And when you sample different types of environments under here, there's a big sort of visual difference between the rounded, large size rock particles, cobbles essentially, and boulders that are in the stream, and the kind of life that you find in this permafrost. So these conduits actually, because it freezes together and squeezes together and disappears and then remelts every spring, you get new permafrost exposed every year. And so this permafrost has been under here frozen for 10,000 years in some cases. And so you might expect that it's going slowly, frozen, right? But you do find dividing populations under there. And what are they doing? They're oxidizing pyrite. Because in this situation, this glacier has, bulldozed its way through terrain that had Proterozoic rocks that had pyrite in them and also had some marbles. So you have not only glacial cave forming, but you also have some carbonate dissolution that's due to pyrite oxidation under here. Okay, let's see, where am I going here? Oh yeah, okay. So I said a little bit about an iron sulfide precipitating biofilm. I'm going to talk a tiny bit more about that because it's an interesting origin of life type of angle and a sort of missing metabolism angle to it. So this is a biofilm that is in the anoxic sulfidic part of the aquifer that we showed you some pictures of before. Excuse me. And it's gray because it has these nano-sized iron sulfide particles in it. It also has, in addition to FeS, it also has FeS2 in two different mineral forms. It has both marcasite and pyrite, and that's weird because they're not supposed to be there in the same place at the same time. So this is the reaction of interest. So there are these iron monosulfide particles, and it's very sulfidic water. It's about half of millimolar sulfide, and there's pyrite precipitating in the biofilm, and you also get some H2 out of the deal, and that's interesting because tons and tons of microbial cells can use H2 to produce energy. And so this is called the Berzelius reaction. It was made popular by Gunther Rechtershauser in the 80s, who proposed that it was the first metabolism. Why did he say that? Well, he said it because both of these things are really common at hydrothermal vents. Reasonable. As origin of life theories go, they're all kind of wacky and short on details. So this is another one like that. No one's ever figured out an organism that can do this, but there's energy available when you do the thermodynamic modeling to ask whether or not something could make a living on that reaction. The answer is yes. In lots of Earth surface environments, this reaction is energy yielding. So it's called a missing metabolism because our general experience is if you put some energy out there on the table, some microbe will come and get it. And if it doesn't, there's an interesting reason why. So we really would like to know who is doing this reaction, or if no one's doing it, why not? So this is a couple more pictures of that same biofilm. It's really spectacular. These kind of ropey formations are like 0.5 meter to 1 meter long, and they're just chock full of pyrite framboids. This is a picture of a framboid that has little grains in it that are marcasite and other grains that are pyrite, which I find really bizarre. There are other bizarre things about this pyrite and marcasite in this biofilm. The individual grains of FeS2 have different trace metal compositions, suggesting that they came from different places, but I haven't figured out how that could be true. So there's some mysteries here. Okay, so I've just given you a whole bunch of different examples of microbes and minerals that are living and forming in caves. There's also this whole other angle to caves, and now there's a planetary caves conference even, which I've never been to, but it's every couple of years, and it's apparently interesting. And there's a couple different kinds of people that are interested in caves on other planets. Some people are interested in whether or not we could live there, because just like any other kind of cells, we do not like the ionizing and UV radiation on the surface of Mars either. So we would like to be, we could either build a habitat that was going to protect us from those, and that's possible. But here's a potential habitat that's already set up to be protected. And so this is an artist's rendition of a lava tube on Mars. I have no idea how realistic this is because we've never been in one on Mars. What else about Mars? Well, there's carbonates present on Mars, but you don't want to imagine that they're going to be in this massive marine bedded carbonate kind of forms. So far, we have not found those kind of carbonates, those kind of cave forming carbonates on Mars. The carbonates that we found are in weathering profiles rather than in a massive form. So for Mars in particular, lava caves are getting a lot more interest and attention than carbonate caves. Okay, I'm going to skip that. These are some images of putative lava tubes on Mars, and I think they're pretty convincing. The shapes of them recall lava flows and de-roofed lava tubes in places like Hawaii. And there's not just one picture like this. There's lots and lots of pictures of these, and these features are more common in this area of Mars that was more recently volcanically active. And so someone has located, for exploration purposes, entrance candidates. So this is a much bigger scale here. So all those red dots are places where you could fly a copter into a lava tube and see what's in there. And this is one of the first images that people pointed to when people asked about lava tubes on caves. Here's a potential entrance. One thing about these things is that the moisture status of them is unknown. So there's a reason why, from a human exploration point of view or a microbial life point of view, you might want to go there and see if there's water, because it's not clear whether there would be or not. We know there's water on Mars. Seems like it's either in the polar regions or underground, but it's not like we have a map of it. So the moisture status of places like lava tubes is not really very well known. Here is one person's idea recently of why there might be water in ice form on Mars. So up here, this is a pressure temperature diagram for H2O, and you can see that Earth is in this awesome place in the diagram where all three forms of water exist and interact. Mars is way down here, so there's either ice or there's vapor. There's not liquid water, and this is a problem for life, right? Because we need liquid. So bear that in mind. But this is a concept diagram showing that there could be water useful for water ice that's useful for humans in lava tubes. Okay, so are Earth caves good analogs for Martian caves? Are there sufficient quantities of soluble rocks on Mars to form caves? And then what about lava tubes? We know there's lava tubes, so those seem interesting.